Man. How are you guys? Good day? Yeah? 29 days spring break. Nice. Yeah. Less than a month.
And then we're out of school shortly after that.
Uh,
Well, I mean, kind of.
it'll pop up to another. When we get back, they'll still be 50 or 60.
Yeah, that's so little.
Oh, it's baby steps. Yeah. And the one day I really need recordings, it just won't record.
Oh, sad. Isn't it weird that we're going to be doing this next year? Does anyone else find
Yeah,
that
that's
super
weird. I feel like we're still
Scary.
freshmen.
That COVID like summed it down. Like,
Yeah.
Yeah.
It's just weird. And then we'll go to college.
It's like one long
So
summer.
excited about it.
Yeah, Nick.
Yeah, exactly. That's weird. It's like
I'm not even 16 yet.
yeah.
Who's 16 in here?
I got 5
I
months.
started.
What's your
I
birthday?
have 6 months.
Is anybody like super young, like you don't turn 16 till your junior year?
Yeah, me. I turned 16 the day after we started.
Oh, that's so
Really?
unfortunate. I'm so sorry.
Yeah, that's a little late. It's all right. So how are we feeling about this stuff so far? Good? Not a big deal? Okay. All right, so today we're going to jump into something a little new. And I think by the end of it, you'll be very comfortable with it. But initially, I'm going to be explaining some whys of things. Just roll with me. And then we're going to start getting into the how we're going to actually look at these. Talking about rational functions. Okay, so I'm going to pull this up. You can look at, I think it's page 67. You want to look in your book. It might be different. Let me see. Seems like it changes every year. I add junk in there. Oh yeah, it's way past that. Okay, so all right, so yeah, page 75. Wow, did add a lot. Okay, so here's the idea of a rational function. And I'm going to build a rational functions mentality on top of what you already know about polynomials. Now, do you remember what a polynomial is? Polynomials are basically this. I know that's an ugly looking function because I have all this A1, A2, but bottom line, a polynomial is stuff like a parabola, an x cubed function, an x to the fourth function. You've been solving a bunch of those in the last chapter, right? X to the fourth plus something x cubed, whatever. Those are examples of polynomials. The key to being a polynomial, though, is that your exponents are all positive integers. So you can't have anything like x to the 1/2, which would make a square root, which would make something over x squared. None of those situations are polynomials. So a polynomial would look like that. Well, a rational function is just a polynomial over a polynomial. That's it. But because you now have a polynomial over a polynomial, and by the way, they don't have to look nearly this ugly. A polynomial, technically, poly, I know you think more than one, right? Like you think monomial means one term. Binomial would be like y equals x squared plus 4 or whatever. But technically a polynomial could still meet this definition and be something as simple as y equals 1. And the denominator, it's kind of another polynomial. It could be something as simple as x. So you already have two rational functions in your list of functions. What are they? The 1 over x function and those are both rational functions. And what you're going to see in rational functions is a couple of things that are different than polynomial functions. Polynomial functions are incapable of having domains that are not all reals. Because if you think about it, polynomials have nothing but x's with positive powers. So there's no square roots. Those positive integer powers. So there's no square roots because those would be like 1/4 powers. There's no x's in the denominator because that would be like x to the -1 or x to the -2. So there's no way to be undefined on a polynomial. All reals. And you've seen that, right? Lines are very simple polynomials. Parabolas are simple polynomials. X cubed graph, those are simple polynomials. They all go forever to the left and forever to the right with no breaks. Rational functions can have breaks. And you saw that on the one over right, they had a what? Right there at y = 0. A vertical asymptote. That was a place where at 0, the graph couldn't go across that vertical asymptote. All right? So when you have a rational function, you're going to see breaks like vertical asymptotes possibly on the graph. You're also going to see situations like what we call holes. A hole is different than a vertical asymptote, but they're both places where the domain is broken. It can't exist there. But if it's a vertical asymptote, it heads towards a vertical asymptote. It's got to either go up or go down, right? On a hole, it basically just runs into the hole. There's nothing there, and then it runs out the other side. And you'll see those holes in those VAs, and you'll be able to tell what is what when you get this thing simplified and broken up. But the first thing I want to talk about before we get into all that is how can you look at a rational function and have any idea? Because what's going to happen, it's kind of like this. And if this helps, maybe it does. This function is a result of two things being divided together, right? It's kind of like if I were to say, hey, I've got 21/4 dollars. Nobody says I have 21/4 dollars. What do they say? I've got $5 and what? 5 cents left over, right? 5 1/4 or 5 1. Nobody says 5 1/4 dollars either, right? But can't I look at this and after dividing, look at this and say, yeah, I got about $5 with a little something left over. You with me? Well, if I want to know what this function looks like, I can do the same thing as I did right here. Here, I divided 4 into 21, and it went with a little bit left over. I can do the same thing here. If I want to know what this graph looks like, I can divide the bottom into the top, which I know that looks terrible right here. It won't be that terrible on the problems we do. I can divide the bottom into the top, and it will give me a whole expression. Now, my answer might be something like x squared plus x, or 2x minus 4, but I'll be able to look at that and tell what the graph looks like. Now, it's also going to give me some remainder. We've seen that, right? Here's what makes a rational function a little bit different than a polynomial. And that remainder means something. But if I want to get the general idea of this graph, I can divide and just throw away my remainder. And let me show you this example, how it plays out. We call this, by the way, when we divide in there to get an idea about what the graph looks like, we call this, depending on the kind of asymptote we get, we call this like an oblique asymptote. Like most people think of asymptotes as just vertical lines or horizontal slanted line. All right, it could be a parabolic curve. Are you with me? So, for example, a parabola, like if I had a parabola would look like this. Say, maybe like this. And that is the actual parabola. But a parabolic asymptote means the graph is going to follow that, but not perfectly. And further right, it's probably going to look really like that parabola. But as it gets in here closer, who knows what might happen? Maybe it follows a vertical up. Maybe it follows that vertical down. But as it gets further right and left, it's going to follow the parabolic asymptote. How will I know it's parabolic? When I divide that into that, if I get a parabola-looking expression plus a weird remainder, tells me what its oblique asymptote would be. right? If I divide that into that and I get a line with a weird remainder, that line would mean that it has something like it would not be a regular line, but it would be a slant. We call it a slant asymptote. That would mean that maybe you have this asymptote that's slanted you're going to follow, which means forever to the right, it's going to really on the top, maybe on the bottom. Forever to the left, it's going to really look like this graph. Maybe on the top, maybe on the bottom. But as it nears the middle, maybe there's a VA in there and it has to dive down or maybe dive up. So when you look at these graphs, most people would not look at this and go, oh, that's a line. They wouldn't. If anything, they're looking at it like, looks more like kind of like an X or something. But if I zoom out further and further and further and further out on Google Earth or something, from far away, all this stuff is going to get so minimalized, all you're going to see it do is follow this line. What line? What parabola? The curve that you get when you divide that into that. So that's one of the ways we can determine the behavior of one of these functions. And I'm using this graph below, or this rational function below, to show you this example. So here we go. So what if I gave you this rational function? You have no idea what it looks like. If anything, you're looking at it and going, wait a minute, that's a parabola, that's a line. But it doesn't look like a paraboline, right? We've got to figure out what this is. So like we did with 21/5 dollars, if I just divide that into that, and if I have to use long division, great. I didn't have to use long division. I could have divided 3, used 3 and done it synthetically, right? If I divide that into that though, notice what I get. I get a 3x plus, I'll get this remainder. So my original function can be rewritten. This right here is the exact same thing as 3x plus 4 plus 10 over x minus 3. Just like 21/5 is the same thing as 4 and 1/5. Are you seeing the analogy? Okay, so what that means is this function is that function. But what does it look like? What it looks like is this. So if I wanted to know, this would be a what? A line that has a slope. So if it has a slope to it, we call that a slanted asymptote. If it had a slope of 0, we'd call it a horizontal asymptote. And if it was a vertical line, we'd call it a vertical asymptote. But I can't get a vertical this way because verticals are x equals, not y equals. I get verticals a different way, which we'll talk about later. So I can look at this and go, okay, even though it might not look like it, it's like a line. The line 3x plus 4. So I go up 4, mark that point, rise 1, rise 3, run 1, rise 3, run 1. It's going to look like that. That's going to be the line, the slanted asymptote that this graph follows. Now, you can't discount this. Clearly, what am I not allowed to plug in this graph? Positive 3 gives me a 0 in the denominator. That is not allowed. That is not in my domain. And you're going to find out later that a positive 3 on this gives me a vertical asymptote. Originally sketched this function, I would have had a vertical asymptote at 3, and this graph's going to be following this line. But look what it looks like initially. I'm going to skip this for a second. On the back, I've graphed it. This is the first graph of this function. Now, it's not this little line in the middle. I put that in there to show the slanted asymptote. It's just the 2 purple parts. But that's what this graph looks like. Nobody on Earth would look at this and go, oh, looks like a line. If anything, they're looking like it, maybe, or parabola down, parabola up, something weird. But look what happens as I go from -30, -30, to -60, -60, whatever, 180, -180. As I keep stretching it out, this curve, as I go further and further away, what does it just start resembling? The line. Now, it doesn't mean this is not here. It still is following that vertical asymptote at 3. See, there's 3 right there. It's diving down and going up. But like for all eternity, remember our window on our graphing calculators is normally like set from -10 to 10. That's a pretty small section of eternity, right? If the graph goes forever right and left, it follows that y equals whatever it was, 3x plus 4. And that's the slanted asymptote. Are you with me? So and that is probably the most popular, I say popular, the most asked question when it comes to math team question is what kind of asymptotes does a graph have? And usually it's a slanted asymptote because when you do that division, you get a line. What you have to remember is if I go back to this, you got to be able to answer it correctly. If I ask what the slanted asymptote is, or what the slant asymptote is, or the oblique asymptote, people use oblique to kind of put all of the asymptotes in a big umbrella, whether it's slanted or parabolic or whatever. It's call them obliques. I went and looked it up, maybe it was last year or the year before, and different websites, different books said different things about oblique. Some people call obliques anything has a power of 2 or higher. Some people call all of them obliques and say if you want to be separate them, you can call them slants or parabolic or cubic asymptotes, whatever. Most of what you're going to be doing is finding slant asymptotes and sketching those slant asymptotes and knowing that the graph is going to follow that asymptote forever to the right. Think about it. As I start plugging really huge values of x in here, think about it. Right here. I'll tell you what, I got a chart for this. Look at this. Here is the original function. Here is only the slant asymptote part of the function. So you'll notice I've thrown away the remainder in the divisor. Do you see that? See it? Now watch, I'm going to start with numbers like 5. 5 in here gives me 24. 5 in the slant gives me 19. To the origin, it is not the same thing, is it? Huge difference, 5 points difference. Those aren't even close to being marked at the same place. I jump out to 10, plug 10 in there, 35 3/7, 34. The gap is closed a little bit, right? Plug in a 20, 64.59, 64. It's getting closer and closer to the slant. I go out as far as 100 or 1,000. I'm off by a 0.1, a 0.01. The graph, as you move forever out, right and left, gets closer and closer to the slanted asymptote. That's the behavior of it. And sometimes I'll ask you a question like, hey, what's the left-right behavior of this? Meaning, what's the graph doing as you go forever to the right and forever to the left? Well, do you know what this is doing when you go to the left? What's 3x plus 4 doing as you head to the left? What is its y? What are its y values doing? So as you move to infinity, what's the y value doing? Going up to infinity. That would be the behavior of the graph. You could say, hey, my right behavior is I'm moving towards infinity. What's my left behavior? I'm moving to negative infinity. What if you had divided this and got a parabola? Like what if you had gotten 3x squared plus 4x minus 2? What do you know about that parabola? What's the left-right behavior? It's going to infinity to the right, infinity to the left. That would be the behavior of this graph. You can tell that by looking at the slant. This would not be a slant, right? Because it's not a slanted line. It would be a what? You'd call it a parabolic asymptote, or maybe you just call it oblique. But you would know that it's a parabolic-looking asymptote, which means this graph, if it was that on the slant, would mean it's got to follow that asymptote as you zoom way and way and way out. Now, I'm not going to make you go back and make this a test about graphing parabolas. I'm not. But you will have to be able to graph slants, but I feel like we're all pretty good with sketching lines. All right? So anyway, that's going to be the first thing that you're probably going to identify. Now, all graphs do not have slanted asymptotes. They don't. The only reason I ended up with a slant asymptote was because when I divided, think about this. When I 3 into this, it went how many times? The first number I put up there was 3x, right? The only way I can get an x there is if what? That power is bigger than that one. What if this was x squared minus 3, and that's 3x squared? Then what happens when I divide that in? Get a 3. That's just a constant. Now, I'm going to still get some remainder, right? I'm still going to have to put the remainder over this. But if I want the slanted asymptote, it's no longer slanted anymore. What is it? It's horizontal. Are you with me on that? What if the power on the bottom is bigger than that? What if it's like x cubed? What happens when I try to divide an x cubed? And I know I would put zeros in there, but What happens? Wait, it doesn't even go in there at all, does it? What kind of asymptote is that? Also horizontal. It's just not higher. It's right there at y equals 0. You're going to learn all these rules about horizontal asymptotes, but the only time you even have to worry about it having a slant asymptote is if you're able to get something other than a number or a 0 there. And that only happens if the power of x on the top is what? Greater than 1 on the bottom. And if it's greater than 1 on the bottom, you're going to have some kind of asymptote that's not horizontal. Okay? Might be slanted, might be parabolic, might be something else. So anyway, I wanted to talk about this and give you a little bit of practice with this. So scroll down, but that's all I'm talking about right here. So I'm going to give you some examples. Right here it says find the slant, the horizontal, or whatever kind of asymptote this thing happens to have, going left to right. And you can do the same thing every time, which is divide. Now, if you see that you can do synthetic division and you like that better, knock yourself out. But you'll see the long division is not a big deal. But I'm going to do synthetic if I can. So can I do synthetic here? Yeah, why not? So I'm going to use positive 1. I'm going to divide it into 2, negative 3, 5. Drop the 2. 1 times 2 is 2. Add negative 1. 1 times that's negative 1. Get a 4. Now, what does this mean?
Remainder.
So there was a remainder 4. So what does that mean? This means y equals 2x minus 1 plus 4 over x minus 1. Now, is this right here my slant asymptote?
No.
No, that is what? That is another way of writing this. Same thing, just written as a mixed number, basically. Right? This is like an improper fraction, and this is like mixed numbers. 21 fourths, 5 and a fourth. This is the same thing. But if I want the slant asymptote, what do? I just take y equals 2x minus 1. So that means this graph looks like that line as you move towards infinity and negative infinity. As you move forever to the right, forever to the left, it's going to resemble this line. What's going to happen in the middle, though? Can you see right now what's going to happen in the middle? What does that tell you? Can I have anything at x equal 1? So there's going to be something, probably a vertical asymptote there, which means as you're looking like this line, is this line, it comes in from the right and the left, and you get closer and closer to x equals 1, it's probably going to separate like this and have a vertical asymptote there. All right? But that wasn't the question. We're good. Just don't keep this with that. What about this? What do you want to do, long or synthetic? You remember what you have to do if you do synthetic on this stuff? You got to go back and divide by that 2, don't you? So I'm going to ignore that right now. This when I set it equals 0, I get 1/2. Here we go, 4, negative 6, 10, 8. Drop the 4, half it's a 2. Add negative 4, half it's a negative 2. 8, half it's a 4. And then don't forget to go back and divide those numbers by 2. Put the 12 over the 2x minus 1. And then put in your x squared, your x, your constant, and clean it up. Now, what is my asymptote? It's not the whole thing, is it? No, the whole thing is just another way. Like if I write this, this is just another way of saying f of x. These are the same 2 things. If I want the asymptote, I'm just using this part. That is the asymptote. And it's not slanted, is it? No, it's parabolic. And again, I'm not going to make you graph parabolic asymptotes and then sketch the graph. I'm not going to do it. All right? And neither will we in pre-calc. So right here, that would mean that somewhere you're going to have this graph that's going to be following that parabola forever to the right, following it forever to the left. So because I know that parabola is going up, I know the right and left behavior. What's the right behavior? Up to infinity, left behavior. Up to infinity. You just learned a little calculus. All right, that's a limit, which we introduced in the pre-calc, but it's a calculus topic. Talking about how And then right here on number 3, I threw this in here, and this is going to kind of introduce you to horizontal asymptotes. Because if I were to do this, would I be able to use synthetic division? No, so you'd be forced to use long division. Now, I hope that you won't do this moving forward, but I want to show you that it still works. If I want to find the asymptote, the behavior that drives left and right, I can divide that into this. And tell me, what do you do first? 3. Okay? Now, if I were to keep multiplying, by the way, notice I don't have an x squared. I can put a 0 in there. The thing about putting the 0 in there, it helps me not make this mistake that I just did right here. Right there. As long as you're careful and line these up, you don't really have to have a 0 there. Are you seeing this? And if you put a 0 in there, then you would have 0 and then negative 6x plus 3. Change my signs, and I get 0 and negative 4x squared plus 11x minus 4. Now, how could I rewrite this function? 3 plus negative 4x minus 4, all of that over 2x cubed minus 2x plus 1. That's f of x right there. But what's my asymptote? Y equals 3. So I didn't have to do any of this. The second I write a constant down, I'm done. Literally, I could have said that goes up 3 times. I guess I'm done. Y equals 3. I didn't have to do all of the junk. So this is not slanted, though, is it? What's y equals? It's horizontal. So what I want you to know, is there another way you can just eyeball this and tell that it would be horizontal? The powers are the same. That's one way it's horizontal. And then how do I get 3 out of that? Does that make sense? So if I see that the powers are the same, I don't even have to do the division. I can say, wait, highest powers are the same. Set it equal to y. That would be my horizontal, not slant, not my horizontal asymptote. Y'all seeing this? And again, these asymptotes I'm talking about, this is going to determine your behavior as you go forever to the right and as you go forever to the left. And let me show you why it gives you this. This is what they do in calculus to prove this. They go, all right, I want to know what happens as I go like way to the right, like infinity. What is this function doing as I go plug an infinity in there? Well, it's kind of hard to think that way, because if I plug an infinity in there, I get infinity cubed, which is what? Infinity, and infinity times 6 is infinity. I'm not getting anywhere, am I? Okay, so how about this? Mathematically, am I allowed to divide the top and the bottom by, am I allowed to do that to a fraction? Because if I divide the top and the bottom by the same thing, that's the same thing as doing this, isn't it? Like if I had the fraction 7/2, if I divide the top and the bottom by the same thing, isn't 7/5 over 2/5 still 7/2? Isn't it? Are you seeing this? The math's the same. Well, what if I divided the top and the bottom by? And you'll not have to do this. I just wanted to show you this. This is kind of an intro to calculus too. Since this is a pre-AP class, I'm doing some pre here. How does this simplify? 6x cubed over 6x cubed is just a 6. 4x squared over x cubed is a what? 4 over a single x. 5x over an x cubed is a 5 over an x squared, and that is, nothing's changed, right? Now, what happens here? 2 over that cancels. Next one, 2 over just an x squared, and then that doesn't do anything either. Now, now you can think about it. What actions now? Now remember, I'm trying to find a behavior of this graph as I go forever to the right. What happens if I go to infinity now? What is 4 divided by infinity? Think about it. I have 4 pieces of pizza. I have to divide it by a massive number of people. What do you get? Not much. Pretty close. 5 divided by infinity squared. Pretty close to nothing, right? 1 divided by infinity cubed. Pretty close to nothing. Would it matter if I plugged a negative infinity in there? I mean, the negative sign is going to change that to a positive, but you're still going to have 4 over an infinity, right? Which is, so what happens to all these fractions? Close to nothing. And all that's left is what? That's why I can look at these and just grab the 6 and the 2 to find the horizontal. Because the horizontal is telling you what's happening as you go forever that way and forever that way, as you plug in massively big or massively small numbers. And that's true for the slant as well. Are y'all seeing this? A little bit? So I hope if I were to say find the horizontal, thing you do is look up here and go, wait, if the powers are the same on the highest powers, take the coefficients and be done with it. Literally, don't do any of this. Do this. Walk away, say y equals 3. Now, let me change this just a tiny bit. With that same thing in mind, what happens if this is a 2x to the 4th? What if I'm going to do it again, what if I were to divide everything to the 4th this time? What is that when I divide it by x to the 4th? That divided by x to the 4th. Go with me? That divided by x to the 4th. And then lastly, this divided by x to the 4th. What happens when I divide all of these by x to the 4th? Tell me if you're with me. You agree? Now, what happens if I plug all the fractions go to 0? What am I left with? 0 over 2. What's 0 over 2? All 0. Would it matter whether that was a 2 or an 8 or an 18 or anything? No, because no matter what it is, it's still going to end up being 0 on the top. So what is your horizontal asymptote? Y equals 0. You got to write it as a line. Horizontal is 4. It's got to be a linear asymptote, right? So say y equals 4. Well, you just learned rules for horizontals and slants. When do you have horizontals? When the powers are the same. And when the powers are the same, all you have to do is say y equals coefficient over coefficient. When else do you have a horizontal? When powers are bigger on the bottom. And what? Y equals 0. And then when do you have slants or maybe some other kind of asymptote? When powers are bigger on the top. And to find those, you have to divide. Those are your 3 asymptotes that deal with behavior to the right and to the left. And that's what the graph is doing to all eternity. It's either following a slant, a horizontal, perhaps a parabola, something else. Right. And that is your introduction to limits that you'll get in May or late April of next year, most likely. And you'll also do that in calculus as well. All right. So that's the first thing we do. And once we find that, we go over to our graph. And like in this case, where if the power was a 4, I would go in there and go, all right, I would mark that horizontal in there. And I know that the graph, I don't know what's going to go on in here just yet. But I know on this one, as I move right along that asymptote, not touching it, but really, really close to it. Maybe on the top, maybe on the bottom. I'll have to know more information to know that. Same thing going left. And that's how asymptotes behave. Now, there are exceptions, like exponential graphs. They're not polynomials, are they? And they're not rational functions. They're a different kind of function. Well, sometimes they only follow an asymptote one way. Like you see exponential, right? They just follow an asymptote that way, but maybe not this way. So that's possible too. And when you get into uglier graphs, sometimes they'll going one way, slant going the other way. Like you'll see it flatten out over here, but then rise up over here. But again, that's above our pay grade right now. You seeing this? Okay, what about, I don't want to go too far. Okay, so if you flip over to page right here next, let's talk about holes. Holes are kind of evil in a way because they look to kind of trip you up, mess you up, and if you don't address them immediately, they cause you pain and sorrow down the road. Okay, so a hole, different from an asymptote, is still a place where the graph can't exist. A hole is going to come from the denominator, just like a vertical asymptote is going to. But you got to, now, if you ever forget all these rules, by the way, look at these notes. They're really nice. You find a hole. It literally is going to tell you what to do if you forget. All right? So first thing you're going to do is you're going to look at this. Here's an example of a rational function, and you're going to factor it. By the way, no, I am not going to give you giant polynomials and ask you to factor them. I will probably already have them factored for you. Because to do that, granted, you know how now, but you would have to go do all the possible rational roots and all the synthetic division. I'm not going to make you do that. And if you couldn't find the roots, then you couldn't answer the questions. But here's how you identify holes. So check it out. Holes. Once you factor the numerator and the denominator, bam, completely. If there is a common factor in the numerator and the denominator, the same factor shows up, that indicates a hole. You must address these first. So when I look up here, I go, wait, I have an x minus 2 and an x minus 2 there. What it means is that at x equal 2, somewhere at x equal 2, there's a hole in the graph. So what I'm going to do is I'm going to try to find that hole. Now that hole is the absence of a point. So I'm going to write the hole like it's a point, but it's not there. Are you with me on that? So I need to know where it is. It's not like a vertical asymptote that I can go, oh, at x equals 2, there's a VA. No, I got to go where at x equal 2 is this graph going to have a hole. So the first thing I know that at x equal 2, so I'm going to take this factor, set it equal to 0. That was pretty easy to see. I know there is a point with an x coordinate of 2 that is my hole. If there was more than one matching factor, then there would be more than one hole. Okay? Now, how do I find the y factor? How do I find the y value that goes with that 2? How do I ever find the y value that goes with the x value? Plug it back in right now, what happens? I get a 0 on the top and a 0 on the bottom, and everything goes to 0 over 0. So what do you think I do? Plug it into the rest of them. And while you're at it, once you identify that 2, cancel these out and never look at this again. Literally. Erase it from your memory. If you leave them in there, you're going to think they're vertical asymptotes later. You're going to think they're x-intercepts later. They're going to get in your way over and over again, and it's going to cost you points multiple times. So the second you see a match, write down the value as x, get rid of it, and then now go back and plug the 2 in and see what the y coordinate is. So what happens if I plug a 2 in here? I get 2 times 3 times a -1, which is -6 on top, and I get 4 times 1, which is 4 on the bottom. So that gives me the point 2 comma -3 halves. So I will now be able to go to my graph, go over 2, down 1.5, and I'll not put a point there. I'll put like an open circle to show the absence of a point. But unlike a vertical asymptote, the graph is literally going to go into that hole on one side, out the other, just like it was a regular point, but it's not a point. Are y'all seeing that? And you, go ahead.
It's just 1 point, right?
It's just 1 point because there was one set of factors. Okay? Now, all these other factors mean something else. We'll get to those in a second. So if you forget, set the canceled factor equal to 0, right, to get the x coordinate. Then plug the x value back into the uncanceled part, in order to find the y value, and that represents your hole. And if there aren't any holes, no worries, you don't have it. Okay? Next thing, horizontal asymptotes. Guess what? We've already talked about this. How do I look at a graph and tell horizontals? There's two ways. So if the biggest powers are equal, what do I immediately know? And that, by the way, is part 2. If the powers, the m and the n, right? If the m and the n are equal, then what do? Y equal coefficient over coefficient. Done. That means you have a horizontal line at whatever you get. If you get y equals 3, go up 3, put a horizontal line. If you get y equals a half, go to a half, horizontal line. If you get y equals -6, horizontal line. Are you with me on that? Now, that's one way to get a horizontal. Second way, what do we say? If the power is bigger on the bottom. If the power is bigger on the bottom, it's always what? Y equals 0. Super easy. You get y equals 0, you draw a horizontal line, y equals 0, which is basically the x-axis. Put a dotted line there. Always put dotted lines for your asymptotes, by the way. Now, what if the power is bigger on the top? Well, it's not a horizontal. It's a what? A slant, most likely in the work that we're doing, would be a slant. Because I'm not going to make you graph parabolics and stuff like that. So that leads you to this. If the power on the top is bigger than the bottom, then you don't have a horizontal, which is fine. You're going to have either a horizontal or a slant. You're going to have one or the other in the work that we do. So you just move to the next step, which is what we've been talking about all day. Find the slant asymptote. And how do you find the slant asymptote? Divide. And what do you do with the remainder after you divide? Toss it. Don't use it. Just divide until you hit the constant, and you're done. Y equals that. Remember, you got to be doing y equals y equals y. And once you have it, you can sketch that on your graph. Again, dotted line. Now, last couple things. Verticals. I have to move a little quickly. Vertical asymptotes. Now, we've already canceled out one set of factors that were holes, right? The vertical asymptotes are the other places where the graph doesn't exist. Where do you think that's going to come from? Where do places not exist? Holes, which you've already addressed, are what? Other places where it could be 0 in the denominator. So for vertical asymptotes, I'm just looking at denominators. So anything left in the denominator, set it equal to 0 and solve. And whatever you get in this case, because you're setting factors that have x's in them, you're going to get things like x equals 2, x equals -1. What do they graph like? What does x equal 2 look like on a graph? Vertical dotted line, right? Those are your vertical asymptotes. And you would mark those. Okay? So again, if you define them, set what is left of the denominator after you've canceled out the holes equal to 0. Set those equal to 0 and solve. And if there are multiple vertical asymptotes, great. Okay? Now again, unless there's also a factor just like in the numerator which cancels out and becomes holes, but you hopefully you've already dealt with that. Y'all with me on this? Okay, I also made a comment right here. If you ever have a squared factor in the denominator, like you did on the volcano, if it's squared, then instead of doing this, they almost always do this. Like remember the y over x. There's one factor down there, x. Set it equal to 0, you get x equals 0. Dotted line right there. The graph did this, right? Or maybe this. If it's squared, it volcanoes. In fact, anytime it has an even power, it volcanoes on the asymptote. Anytime it has an odd power, it goes in different directions on the asymptote. That's important to see that. So if you look down there and you look at the denominator and you see an x minus 2 squared, that means the root you get at x minus 2, which should be the vertical at x equals 2, it's going to either follow it up on both sides or follow it down on both sides. But if you just see a single factor like x minus 2 on the bottom, then it's going to do this. Are y'all with me on that? And you can use what you know about 1 over x and 1 over x squared to kind of help you remember that. Last couple things. X-intercepts. Let me ask you a question. When do you get an x-intercept? Or what do you know about every x-intercept on the planet? If it's an x-intercept, the y value of that point is a what? 0. So technically, to get an x-intercept, all I would have to do is let the y value be 0. Now I have a question. When can a fraction equal 0? When the top is 0. So really, all I have to do to find my x-intercept is do what? Set the top part equal to 0. So whatever the factors on the top, when I set them equal to 0, I get x-intercepts, which are points. The factors on the bottom, I set them equal to 0 if they're not holes. I set them equal to 0, and they give me vertical asymptotes. And if they match on the top and the bottom, they give me holes. Right? And then you get your slant, your horizontal, like we described earlier. And then y-intercepts, there's only going to be one y-intercept at most. Because if there were two y-intercepts, it wouldn't be a function, right? It wouldn't pass the vertical line test. So the y-intercepts, I don't know why I said intercepts, but the y-intercept, all I have to do there, every y-intercept has an x value of what? So I just plug a 0 in for x and everything and simplify. And you can mark that as well.
Can you have a hole like through a vertical asymptote so you go through?
I will never have a vertical asymptote and a hole in the same place. But if I did, like you don't, but if it looks like it based on the graph, the vertical asymptote trumps it. All right? So real quickly, I've got 3 minutes. Let's just take a look at this real quickly. And this is what I want you to be able to do, so do your best on the homework. But I would have to factor it first. If you stink at factoring, you probably know that. You probably need to come and get some help from me. And I would definitely do that. So what do I see immediately right there? What do I see right there? So there's a hole, okay? So if there's a hole, where would the hole be located? At -2, but wait, I cancel it out. And what do I have to do now? Plug that back in, I get -9 over -1, which is 9. So at -2, up 9, I have a hole. I'd mark it like that. I'll do better about getting them on the graph. Now, what is this? Does it have a horizontal or a slant? Why? How is the same? What is the horizontal? Y equals coefficient over coefficient. Y equals 1. That means there's no slant because there can only be one or the other. Is there a vertical asymptote? Whatever's left in the denominator. Right? Go look at these rules tonight. Look at the denominator, set it equal to 0, x equals -1. You tracking? Is there an x-intercept? Whatever you have in the numerator. So the x-intercept, 7 when y is 0. Does it have a y-intercept? Plug in 0 for x, and what do I get when I plug in 0 for x? -14 which is -7. 7, 0, 0, -7. Now, from this information, I think I have enough to sketch this graph. Because what do I know is happening as I go this way? I got to follow the horizontal or the slant, whatever it has. So, and do you think I'm going to go down here?
No.
Why not?
Cross the line.
It would cross that. And guess what? There are no x-intercepts except over here. This is the only way to cross the x-axis right there. So what does that mean? It must be somewhere up here, and it's got to go through that hole, right? And it must be that. Now, I asked you right here to plot a couple extra points. Pick a couple extra values like -3. Plot a couple extra points to be really exact or get better. And then what do you think happens here? It's got to cross there, right? Follow it out, and it's got to also hit this point and dive down that asymptote. Hey guys, get started on these, see what you can do. We're going to continue talking about them tomorrow. Y'all have a good one. Yeah. Well, honestly, dude, that was a one-day lesson. You can watch the video. It was literally a take-home lesson where you were supposed to go, and if you saw, I don't know if you saw the video, you can go back and look for it. But it said you were supposed to go home and read that whole packet. All right, and then once you had that, they basically came back and asked questions. If they had any questions, I don't think anybody asked anything. And I just did some random examples, which are on the video. And that was it. And there's a review on there. There's some practice problems in the book. And there's a review on there that's probably fairly similar to your test. But you just need, at this point, again, it wasn't like we covered this for 3 days. It was a go home and read this, come back and ask questions, quiz the next day.
Okay, so is there going to be a time I can take it? Or...
You'd have to take it during the makeup testing.
Okay.
So you have to either come in the morning. Well, you just took a test in the makeup, right? Yeah, same thing. Pick a day and go. It's already in there. But if I were you, when you do the classwork and you do the practice review sheet, if you don't know what you're doing, come see me. Right, just make sure because there's some couple quirky little things in there. But it was really more of a take-home assignment than anything, in a one-day review that we had. All right, but come see me if you got questions before you take it. Yeah.